Yesterday we wrapped up working with exponential and logarithmic equations, and today you're going to look at some applications with some real world scenarios. Some important formulas that you're going to want are first compound interest, which is probably the most fundamental of the exponential functions that we use in everyday life, and it is a of t is equal to p times 1 plus r over n raised to the power of n times t, where all of these variables represent a of t is the amount after t years, p is your principal or your initial investment, where you start. R is going to be your interest rate. And the number one mistake is that you don't convert to a decimal. Make sure you always convert any percentages to a decimal equivalent by dividing by 100. N is the number of times you're compounded. So if you compound your interest quarterly, then that's 4 times per year. If you compound it semi-annually, then it's 2 times per year. If you compound it monthly, then it'll be 12 times per year. And t is your number of years. Another interest formula that you often use is continuous compounding. And this is when a lot of credit card companies use this method for calculating interest on your credit card bill. So you find your continuous compounding. It is a of t is equal to p times e raised to the rt, where e is that number, 2.7178 approximately, that has a key on your calculator. So a of t, again, is equal to the amount after t years. P is still your principal or your initial investment, where you start from. R is still your interest rate, and it still must be converted to a decimal. And t is still your number of years. The difference between the two is that you will not be compounding monthly, quarterly, semi-annual. You're essentially compounding every minute of every hour of every day. So this one takes on a different form. And then two others that you're probably exceptionally familiar with just since Algebra 1 when you started studying the different types of functions. You have exponential growth. So you have p of t is equal to p naught, that p sub 0 we refer to as p naught, times e raised to the rt. And you say, well, that looks a lot like continuous compounding. Indeed, it does. But our p of t represents our population after time t. Our p naught is our initial population. R is our growth rate, again, as a decimal, and t is the amount of time. And then if you have exponential growth, then of course you have exponential decay. So with our exponential decay, It actually looks a little bit different at this level because we use it for so many things, specifically at the chemical and physical level in biophysics and chemical engineering. So we have m of t is equal to m naught times e to the negative rt. So this is m of t is the mass remaining after time t. M naught is your initial mass, or the mass you start with. R is going to be your decay rate, again as a decimal. And T is going to be your time. So in the next video, we will work through several examples of working with these, converting between the exponential and the logarithmic form, and applying them to some real-world applications. And you will have a set for you to try on your own before you do the homework tonight as well.